Look up at the sky on a clear night. There it is. That pale, pockmarked disk floating above you, close enough to seem almost touchable, far enough to remain forever out of reach. You've seen it your entire life. So have your parents, your grandparents, and every single ancestor stretching back through all of human history. The moon has been there for so long that we have stopped noticing it. We glance up, perhaps register it in passing, and then look back down at our phones. But stop for a moment. Truly look at it. Because what you are seeing is not simply a rock in the sky. It is a gravitational anchor, a tidal engine, a shield, a clock, a lantern. The moon is quietly responsible for almost everything that makes Earth the living, breathing, storm-swept, life-saturated world you call home. And yet, for all its importance, it is barely a whisper in the grand cosmic scale of things. The moon is a small body, a fragment really, knocked loose from the young Earth in a catastrophe almost beyond imagining. Everything about it is a consequence of violence, and everything about your life is a consequence of it. So let's ask the question that sounds like the beginning of a nightmare, but is actually the beginning of one of the most staggering journeys in science. What would happen if the moon hit the Earth? Not drifted away, not dimmed, not vanished overnight, but hit, came back, returned home in the most catastrophic reunion in the history of the solar system. The answer is not simple, it is not quick, and it is not just about fire and explosion, though there will be plenty of both. It is a story that begins 4.5 billion years ago in a swirling cloud of gas and dust, passes through the whole of Earth's living history, and arrives finally at a question that redraws the map of everything. In the autumn of 1969, a geology professor at the University of California sat down with a small box of rocks that had been delivered to his laboratory by courier. They were unremarkable in appearance. Gray, dusty, some of them not much larger than a thumb. But they were the most precious geological samples ever collected because they had come from the surface of another world. They were moon rocks, returned to Earth by the crew of Apollo 11 just months before. Professor Gerald Wasserberg spent weeks analyzing them with the kind of meticulous care usually reserved for holy relics. And what he found in those gray fragments was astonishing. The rocks were ancient beyond comprehension, around 4.4 billion years old, almost as old as the solar system itself. But what made them truly extraordinary was their composition. The oxygen isotopes inside them were identical to those in Earth rocks. Not similar, identical. In all the solar system, no two bodies share the same isotopic fingerprint. Not Mars, not Venus, not any of the asteroids so far studied, except the moon. The moon and the Earth are made of the same stuff, and that discovery, quietly confirmed in a university lab in California, is the foundation of everything that follows. Because it tells us that the moon did not arrive from somewhere else. It was born here. It was born from us. The leading theory for how the moon formed is called the giant impact hypothesis, and it is exactly as dramatic as the name suggests. Around 4.5 billion years ago, when the solar system was still young and chaotic, a planet roughly the size of Mars wandered into Earth's orbital path. Scientists have named it Theia, after the Greek Titan who was the mother of the moon goddess Selene. The collision that followed was not a gentle, grazing blow. It was a near head-on impact at tens of thousands of kilometers per hour. The energy released was incomprehensible. Both bodies were partially vaporized. Vast clouds of superheated rock and gas were flung into orbit around the battered, half-molten Earth. And over the course of just a few thousand years, those clouds of debris coalesced under their own gravity into a new body. The Moon, born from Earth's own flesh, flung into the sky by the most violent event our planet has ever endured. So when you ask what would happen if the Moon hit Earth, you are really asking what would happen if that ancient story ran in reverse. If Theia came home. But before we can understand the end, we need to understand exactly what the Moon is doing right now. Because it is doing more than you might think. Right at this moment, as you read these words, the Moon is pulling on the oceans of the Earth, not gently. The gravitational grip of the Moon generates tidal forces that shift literally quadrillions of tons of water twice every day. The tidal bulge on the ocean surface facing the Moon is roughly 60 centimeters higher than the surrounding sea. That might not sound like much in the middle of the ocean, but on coastlines, funneled by geography, it becomes something else entirely. In the Bay of Fundy in Nova Scotia, tidal fluctuations can reach 16 meters. Ships that were floating peacefully at high tide find themselves resting on exposed mud at low tide 6 hours later. The Moon is doing that every single day, relentlessly, without pause, for over 4 billion years. And that tidal interaction has done something even more profound than simply moving water. It has slowed the Earth down. In the earliest days of our planet, shortly after the Moon formed, Earth rotated so fast that a day lasted only 6 hours. The young Moon hung enormous and close in a sky that wheeled at dizzying speed. But over billions of years, the friction of tidal forces has acted like a vast cosmic brake. Angular momentum has been gradually transferred from the Earth's spin to the Moon's orbit, which is why the Moon is slowly drifting away from us at a rate of about 3.8 centimeters per year. Today, a day lasts 24 hours. Life evolved in that rhythm. Our circadian clocks, the biological timekeeping buried in every cell of your body, are calibrated to that 24-hour cycle. Remove the Moon, or change its position dramatically, and you change the length of the day. You change the rhythm of life itself. The Moon also stabilizes Earth's axial tilt. Right now, our planet tilts at approximately 23.5 degrees relative to its orbital plane. That tilt is what gives us seasons. But without the Moon's gravitational steadying influence, computer models suggest Earth's axial tilt could wobble chaotically between near 0 degrees and more than 85 degrees over millions of years. A tilt of 85 degrees would mean the poles face directly toward the sun for part of the year, and directly away for the rest. The equator would freeze. The poles would bake. Seasons would not simply be a matter of warmer summers and colder winters. They would be civilization-ending extremes. Mars, which has no large moon, has indeed experienced this kind of axial wandering over geological time. Earth, stabilized by its lunar companion, has not. The moderate, relatively predictable climate in which complex life evolved and human civilization was built is, in no small part, a gift from the Moon. Now imagine all of that changing, not gradually, but catastrophically. Imagine the Moon is no longer drifting away from Earth at 3.8 centimeters per year. Imagine instead that something has reversed that drift, that the Moon is falling. The mechanism for such an event, could come from several directions. A rogue planet passing through the inner solar system could perturb the moon's orbit. A large asteroid impact on the moon at just the wrong angle and velocity could steal enough orbital energy to send it spiraling inward. In theory, a sufficiently powerful gravitational interaction with another massive body could achieve the same result. These scenarios are extraordinarily unlikely, but the solar system has surprised us before. And besides, the purpose of asking this question is not to worry. It is to understand. Because the story of what the moon does to Earth on its way down is, in its terrible way, one of the most illuminating stories in all of planetary science. When an orbiting body begins to lose orbital energy, it does not fall in a straight line. It spirals. The moon would begin its descent gradually, over perhaps hundreds of thousands of years. In those early stages, the changes would be subtle. The moon would appear very slightly larger in the sky. The tides would grow incrementally stronger. Nothing that any single human lifetime would notice, but the animals would. Species whose breeding cycles are governed by lunar phases, sea turtles, coral reefs, many fish, countless insects, and marine invertebrates would begin to find their biological rhythms disrupted. Coral bleaching events tied to tidal stress would increase. Coastal ecosystems would begin to show strain. The ocean floor, already sculpted over millions of years by tidal patterns, would begin to change as new current regimes took hold. This is the slow phase, the polite overture before the symphony of destruction begins. But let us follow the moon further in. As it descends and the distance between it and Earth decreases, the tidal forces rise steeply. Tidal force is not proportional to distance. It scales with the cube of the distance. This means that when the moon is half as far away as it is today, the tidal forces are not twice as strong. They are 8 times as strong. When it is a third of the current distance, they are 27 times as strong. And as the moon draws close enough, something truly extraordinary would begin to happen to the oceans. Picture yourself standing on a coastline. Today, high tide might bring the water to your knees. But as the moon draws closer over those long intervening years, high tides have grown, first to waist height, then over your head, then to the tops of buildings, then to the tops of hills. The oceans would begin to migrate. Coastal cities that have stood for centuries would find themselves permanently submerged, then partially, then completely. The tidal zones would not simply shift. They would become vast, sweeping, catastrophic floods that race across continents twice a day, scouring everything in their path, retreating, then returning, relentless and growing. The city of London sits at roughly 11 meters above sea level in many of its oldest districts. New York City's financial district sits at around 4 meters. Shanghai, one of the most populous cities on Earth, sits at an average of about 4 meters above sea level. None of them would survive the tidal amplification of a falling moon. Long before any rock reached the atmosphere, the oceans would have already redrawn the map of human civilization. But there is more. The moon's gravitational pull would not just affect the liquid oceans. Earth has something called solid earth tides. Right now, as you sit reading this, the rock beneath your feet is being pulled slightly upward by the moon's gravity, flexing by about 30 centimeters as the moon passes overhead. You never feel it because everything around you is rising and falling with it. But as the moon approaches and tidal forces multiply, those solid Earth tides would grow. The ground itself would begin to heave. Fault lines already under stress would be triggered. A planet that today experiences around 500,000 detectable earthquakes per year would see that number climb dramatically. Volcanic systems lurking beneath calderas, systems kept in a delicate balance by the existing tectonic regime, would be destabilized. The supervolcano beneath Yellowstone, the vast magma chambers lurking beneath the Campi Flegrei in Italy, the systems beneath Iceland that have reshaped European climate for millennia, all of them would feel the moon's growing grip. Now we reach the Roche limit. This is the moment when everything changes. In 1848, a French astronomer named Édouard Roche was working through the mathematics of celestial mechanics when he arrived at a remarkable conclusion. There is a critical distance around any massive body inside which a second body held together only by its own gravity cannot survive. Tidal forces tear it apart. For the Earth-Moon system, that critical distance, the Roche limit, sits at approximately 9,500 kilometers above Earth's surface. The Moon currently orbits at an average distance of about 384,400 kilometers. So the Roche limit is not something we think about very often. But when our falling moon crosses that threshold, the mathematics become pitiless. Tidal forces act differently on the near side of an object than on the far side. Gravity pulls the near side more strongly than the far side, because the near side is closer to Earth. For a small pebble, the difference is irrelevant, because its own molecular and gravitational binding forces are far stronger than any tidal differential. But for an object the size of the Moon, the tidal differential across its 3,474-kilometer diameter becomes, at the Roche limit, exactly equal to the Moon's own self-gravity. Inside the Roche limit, tidal forces win. The Moon would begin to break apart, not explosively, not in an instant, but in a grinding, stretching, fracturing process that would unfold over days or weeks. The Moon's near side would be pulled more strongly toward Earth than its far side. The body would elongate, pulling apart along its equator. Cracks would propagate across its surface. The vast lava plains of the lunar Maria, those dark patches visible from Earth with the naked eye, would rupture. The ancient highlands, battered by billions of years of cratering, would shatter, and the Moon would begin to dissolve into a ring. You have seen rings before, on Saturn. Those magnificent, delicate structures are composed of material that either formed inside Saturn's Roche limit or was torn apart after wandering inside it. Earth would have its own rings now. Not as delicate as Saturn's, not as photogenic or thin, a thick, churning, chaotic band of rock and dust stretching around the planet's equator. From Earth's surface, looking up, the sky would no longer show you the familiar disk of the Moon. Instead, a brilliant arc of rocky debris would span from horizon to horizon, catching sunlight and glowing with a light brighter than the full moon ever achieved, visible even in daylight as a blazing ribbon cut across the sky. For a brief period, perhaps hours, perhaps days, Earth would be a ringed planet. The only ringed rocky planet in the solar system, and it would be astonishing. And then the ring would start to fall. Ring systems are not stable. The particles within them are at different orbital distances and therefore different orbital speeds, and they interact, colliding, clumping, and over time either drifting outward to escape or drifting inward to fall. Ring systems are not stable. The particles within them are at different orbital distances and therefore different orbital speeds, and they interact, colliding, clumping, and over time either drifting outward to escape or drifting inward to fall. But before we get there, let us sit with the ring for a moment, because the rings of other planets have something to teach us about what Earth's ring would actually mean for the life still trying to survive below. Saturn's rings cast shadows on the planet's northern hemisphere during certain parts of its orbit. Those shadows are genuinely significant in terms of temperature and atmospheric dynamics. Earth's ring, situated above the equator, would cast a permanent shadow band across the tropical regions, potentially cooling the equatorial zone while leaving the poles unchanged. This differential would drive extraordinary new atmospheric circulation patterns. The trade winds that have governed equatorial weather for millions of years would be disrupted. The monsoon systems of South Asia and sub-Saharan Africa, which billions of people and ecosystems depend upon, would be altered beyond recognition. The agricultural systems of the most densely populated regions of the world, systems that were built over 10,000 years around the predictable cycle of wet and dry seasons, would fail. Famine on a scale that has no precedent in human history would follow. All before a single large fragment of the former moon had reached the ground. There is something particularly sobering about this. The civilization-ending consequences of the moon's return would begin not with fire and impact, but with shade. With the shadow of a ring falling across fields that will not grow. With a disrupted monsoon that does not arrive. With temperatures dropping in places where people depend on warmth and rising in places where people depend on ice. The slow catastrophes are always harder to see coming than the fast ones, and they are often, in the end, more destructive. For a ring composed of material that was originally the moon, the timeline would be geological, perhaps tens of thousands of years, perhaps millions of years in a cold, undisturbed system. But this system is not cold and undisturbed. The ring is falling through the very edge of Earth's extended atmosphere. Friction is present, and friction is relentless. The ring would thin from the inside as the innermost particles encountered atmospheric drag and began to spiral down. What followed would be a bombardment unlike anything in the history of the solar system, since the formation of the planets themselves. Individual chunks of the former moon, ranging in size from fine dust to boulders hundreds of kilometers across, would begin to enter the atmosphere. The dust would come first, darkening the sky globally within days. Sunlight would be filtered through a thickening shroud of debris. Temperatures on the surface would begin to fall. Photosynthesis would slow, then stop. Then, as the larger fragments arrived, the noise would begin. A single impact from a 100-meter chunk of what was once the moon would release energy roughly equivalent to a large nuclear bomb. A kilometer-sized fragment would be a civilization-ending event in its own right, comparable to the impact that wiped out the non-avian dinosaurs 66 million years ago. And those kilometer-scale fragments would not arrive one at a time, years apart. They would arrive in their thousands, then tens of thousands, then hundreds of thousands. They would hit the oceans and generate tsunamis that would make every previous tsunami in recorded human history look like a ripple in a bathtub. They would hit the land and throw columns of molten rock and superheated gas into the atmosphere. The energy deposited into the atmosphere would raise global temperatures to levels at which the oceans themselves would begin to steam. There is a concept in planetary science called a steam atmosphere runaway. It is the process by which a planet like Venus, which may once have had liquid water, lost it all. When enough energy is deposited into the surface and ocean, the oceans begin to evaporate faster than they can cool. Water vapor is a potent greenhouse gas. Its presence in the atmosphere traps more heat, which causes more evaporation, which traps more heat. The feedback loop runs to completion. The oceans boil off entirely. The water vapor eventually photodissociates in the upper atmosphere, hydrogen escaping into space and oxygen chemically bonding with surface rock. A planet that had oceans is left in the end with neither. Venus is the cautionary tale. Earth, subjected to the thermal energy of the moon's disintegrating impact sequence, might follow the same path. But let us zoom in. Let us not deal only in planetary scales and geological timescales. Let us consider what it would actually feel like to be alive on Earth as the moon began to fall. The year is, let us say, roughly 5,000 years in the future. Scientists have known for 3,000 of those years that the moon's orbit is decaying. They knew it from the mathematics of orbital mechanics, when, one day, a slight but measurable anomaly appeared in the moon's trajectory. The tiny outward drift, reliably measured for centuries, had stopped. And then, almost imperceptibly at first, it had reversed. The best orbital models in the world disagreed on the exact cause, though the leading candidates involved a close gravitational encounter with a rogue body passing through the outer solar system, perturbing the moon's orbit just enough to change the direction of angular momentum transfer. Whatever the cause, the consequence was clear. The moon was coming home. For the first 2,000 years, life went on. The moon grew imperceptibly in the sky. Tides increased by a few percent and then a few more. Coastal flood barriers that had been built for sea level rise now found themselves overwhelmed slightly more often than their engineers had planned for. Scientists argued about mitigation strategies. A civilization that had already grappled with climate change, pandemics, and resource scarcity found itself facing one more existential problem on a list that never seemed to get shorter. Some called for a deflection mission to send spacecraft to nudge the moon's trajectory. The mathematics of that proposal were sobering. The moon contains 7.3 times 10 to the power of 22 kilograms of mass. Moving it would require energies that dwarfed anything human technology had ever produced. Not impossible in theory, but practically, given the timescales and the resources required, the project stalled in international committees, as great engineering proposals often do. By the year 3000, the moon was measurably different in the sky. A trained eye could notice it without instruments. Tides had grown enough to make many low-lying coastal cities unlivable. The great coastal migrations had begun. Hundreds of millions of people moved inland. The political and social upheaval of those mass migrations reshaped governments and economies. As it so often has throughout history, catastrophe drove innovation. New cities rose in higher places. New architectures, new power systems, new agricultural models adapted to a world where the tidal rhythms that had governed coastal ecosystems for 4 billion years were now becoming something alien and destructive. By the year 4000, the night sky had changed enough that children growing up had no reference point for what it had once been. The moon was now significantly larger, casting stronger shadows. Tidal bores that had once been tourist attractions in a handful of rivers around the world were now destructive walls of water that penetrated hundreds of kilometers inland twice a day. The global ecosystem, already severely disrupted by the initial centuries of increased tidal stress, was reorganizing. Species that had evolved around stable tidal cycles were in catastrophic decline. New ecological niches were opening, and the organisms fast enough to exploit them were proliferating. Evolution does not pause for an apocalypse. It accelerates. Then came the year 4500 and the Roche Crossing. Nobody alive on Earth had ever seen anything like it. The moon, now occupying a section of sky perhaps 5 times the diameter it had in the ancient photographs, began to visibly distort over the course of a single night. Professional and amateur astronomers watching through telescopes saw the first fractures appear on the lunar surface. Dust plumes rose from the terminator line, the boundary between the sunlit and dark sides of the moon, visible even to the naked eye, as the moon was now so close and so large. Over the following days, the shape changed. The disk elongated. The near side bulged toward Earth. Then the fractures spread, and the ring began to form. The display in the sky that followed was the most magnificent and most terrifying thing any human eyes had ever witnessed. The ring spanned the equatorial sky from horizon to horizon, glowing in every color from deep amber to brilliant white as different minerals caught the light. The nights were brighter than the full moon had ever been. The days had a surreal, diffuse luminosity as light scattered through the ring's dust. Children stood on rooftops and watched in a silence broken only by the distant thunder of falling fragments in the far corners of the world. In that brief window, before the bombardment intensified, Earth was a ringed planet, and it was beautiful. It did not stay beautiful for long. The physics of what followed are, in their merciless way, some of the most well understood in all of planetary science. We have seen the evidence of previous planetary bombardments preserved in the geological record. The Late Heavy Bombardment, a period roughly 4 billion years ago when the inner solar system was peppered with impacts following a rearrangement of the giant planet's orbits, left its scars across the moon's own face. All those craters you can see from Earth with the naked eye are the marks of that era. The geological evidence on Earth is harder to find because erosion, plate tectonics, and biological activity have long since covered most of the early impact craters. But the moon has been preserving the record for us, and that record is not gentle. When the ring began to fall in earnest, the bombardment started at the edges, small particles first, frictioning against the outer atmosphere and burning up, painting brilliant meteor showers across the sky day and night. For weeks, the spectacle was extraordinary. Then the medium-sized fragments began to arrive. At this scale, enough material survives the atmospheric passage to reach the ground, and the energy released by even a modest fragment hits with a force that turns the ground to liquid. Then the larger fragments began to arrive, and the word bombardment became inadequate. What followed was the effective resurfacing of the planet. The geological term for what happens when a planet is subjected to this kind of impact rate is called impact melt flooding. The energy delivered by successive impacts melts the surface rock, which flows like water into the low places, coating them in fresh rock. Beneath that new rock, everything that had existed before is sealed away. The accumulated sediments of 4 billion years of Earth history, the fossil record, the traces of ancient oceans and ancient atmospheres, the chemical signatures of life, all of it smothered beneath a new volcanic surface. The geological clock is reset, not because time has stopped, but because the previous record has been erased. Earth would, in geological terms, become young again, and in doing so, it would become, at least for a time, uninhabitable. Here is where we must sit with a number that is difficult to comprehend. The Moon contains approximately 1.2% of Earth's mass. That seems small. But Earth is a very large planet. That 1.2% translates to approximately 7 times 10 to the 22nd kilograms, which is about 80 times the mass of all the world's oceans combined. When that mass converts to kinetic energy in the process of impacting Earth, the energy released is, in principle, enough to vaporize the entire planet. Not melt, not disrupt, vaporize. If the total kinetic energy of the Moon's infall were deposited instantaneously, Earth would cease to exist as a solid body. It would become a cloud of superheated vapor expanding outward into space, which would eventually cool and condense and slowly, over millions of years, form a new rocky planet somewhat larger than Earth, and probably a new, smaller moon around it, as some of the debris remained in orbit. In practice, the Moon would not deliver all its energy instantaneously. The ring phase would spread the delivery over thousands to millions of years. But the cumulative effect, the total energy balance, remains the same. Earth as it currently exists, with its cool crust and liquid oceans and breathable atmosphere and 4 billion years of accumulated biological complexity, would not survive the Moon's return. The question is only one of timescale and mechanism. But here's the thing about destruction on a planetary scale. It is not, from the universe's perspective, an ending. It is a transformation. Let us go back further. Let us go back to the beginning of our story, to the moment when the Moon was born. Because that formation event teaches us something profound about what the Moon's return would actually mean. When Theia struck the proto-Earth 4.5 billion years ago, the collision produced a disk of debris that coalesced into the Moon. But it did something else too. The collision partially remelted Earth's surface, resetting the geological clock in exactly the way we just described. It stripped away most of Earth's early atmosphere. It mixed and homogenized the materials of 2 planetary bodies, producing the uniquely Earth-like composition that the Moon's identical oxygen isotopes still attest to. And crucially, the angular momentum of the collision gave Earth its spin and gave the Moon its orbit, and the gravitational dance between the two shaped the tidal conditions under which life first evolved. The birth of the Moon was a catastrophe. It was also the precondition for everything that followed. Every living thing on Earth is here because of that ancient impact. The stability of the tides that shaped our coastlines, the length of the day that calibrated our circadian rhythms, the axial tilt that gave us seasons, the reduced axial wobble that kept our climate moderate enough for complex life to evolve. All of it flows from that first violent collision. There is a deep irony in this. The Moon that formed from the catastrophe of Theia's impact went on to become one of the primary conditions for life. It stabilized the tilt. It slowed the rotation. It generated the tides. It absorbed the blows. It taught us to count and to track time. And now, in the thought experiment we are running, that same moon returns and undoes all of it, collapsing back toward the world it helped to build. Creation and destruction wearing the same face, a loop that closes on itself. There is a word in Japanese, mono no aware, that roughly translates as the pathos of things, a bittersweet awareness of impermanence. It is the feeling you get when cherry blossoms fall, when a piece of music ends, when a child falls asleep in your arms for the last time without either of you knowing it is the last time. It is a recognition that beautiful things do not last, and that this is not only sad, but is also, in some way, the source of their beauty. A cherry blossom that never fell would not be a cherry blossom. It would be a piece of plastic. The moon's impermanence, the fact that it is leaving, that it will one day be gone, is part of what makes its presence so quietly extraordinary. And the thought experiment of its return forces us to reckon with what we would lose, which is the only way, sometimes, of understanding what we actually have. And so the return of the moon, the closing of the circle, would be, in a very deep sense, a second creation event, catastrophic for everything currently alive. But potentially, in the fullness of geological time, a reset that could lead to something new. Perhaps not life as we know it. Perhaps not life recognizable to us at all. But in a universe that has shown over and over again that chemistry in the presence of energy and liquid water tends toward increasing complexity, the reformation of a rocky planet from the ashes of Earth and Moon would not necessarily be the end of life's story, only the end of this chapter. There is a woman named Carolyn Porco who has spent decades studying planetary ring systems. As the leader of the imaging team for the Cassini mission to Saturn, she has seen more ring science produced in a single decade than in all the previous centuries of astronomy combined. In 2005, when Cassini first sent back high-resolution images of Saturn's rings from orbit, Porco described her reaction as a kind of religious experience, not because she believed in anything supernatural, but because the rings were so improbably, inexplicably beautiful. Sheets of ice and rock only tens of meters thick in places, extending for hundreds of thousands of kilometers. The rings were a reminder that the universe does not reserve its grandeur for the large and the permanent. The most delicate things can be the most magnificent. Porco has also thought carefully about what Earth's rings, born from the moon's disintegration, would look like from the surface. Unlike Saturn, which is tilted on its axis, and whose rings cross the sky at an oblique angle depending on where you are on the planet, Earth's equatorial rings would appear differently depending on your latitude. At the equator, the ring would appear as a narrow, blazing line cutting directly overhead from horizon to horizon, too bright to look at directly in full sunlight. At mid-latitudes, it would arch across the sky at an angle, its apparent width growing with proximity to the equator. At the poles, it would sit at the horizon or below it, perhaps visible only as a glowing arc. For billions of years, our ancestors lived under a sky dominated by the gradual, reliable cycle of the moon. The humans who lived to see the ring, in the brief window between the Roche crossing and the beginning of the bombardment, would have looked up at something no human eye had ever seen, and no human eye after them ever would again. But let us not end there, because the question this journey leads us to is not simply about destruction. It is about dependence, about connection. about the extraordinary, invisible web of relationships between Earth and Moon that we have spent our entire civilization taking for granted. Consider the tides for a moment longer, not as an abstraction of gravitational mechanics, but as a biological fact. The intertidal zone, that thin strip of coast that is alternately submerged and exposed by the tides, is one of the most biologically productive environments on Earth. It is where ocean meets land, where the chemistry of seawater meets the chemistry of the atmosphere, where creatures adapted to aquatic life have, over hundreds of millions of years, been repeatedly exposed to conditions that favored the evolution of air-breathing adaptations. The intertidal zone is, in a very real sense, where life learned to leave the sea. Without the tides, that zone would barely exist. A tideless Earth would have a shoreline, but it would be a static thing, not the dynamic, twice-daily cycling environment that has been one of evolution's great laboratories for 400 million years. Without the Moon's tidal forcing, the ocean circulation patterns that distribute heat around the planet would be different. The deep water formation processes that drive the global thermohaline circulation, that vast conveyor belt of ocean currents that keeps Western Europe warm and transports oxygen to the deep sea, would be altered. Less tidal mixing means less exchange between the warm surface layers and the cold, nutrient-rich deep. Less exchange means different nutrient distributions for the phytoplankton that form the base of the ocean food chain and that produce roughly half of all the oxygen in Earth's atmosphere. The Moon is in the air you are breathing right now. The Moon is also, in a manner of speaking, in the calendar you live by. The word month derives from the word moon. Our earliest ancestors organized time by the lunar cycle. The roughly 29.5-day interval between successive full moons was among the first natural rhythms that early humans tracked and recorded. The earliest known lunar calendars date back at least 25,000 years, carved into bone, tallied in ochre on cave walls. Long before anyone could write, before anyone could build, people were watching the moon and counting. The moon taught us that time has a structure, that days accumulate into cycles, that cycles accumulate into larger patterns. The intellectual foundation for mathematics, for astronomy, for agriculture, for civilization, rests partly on the simple, repeated observation of a light that waxes and wanes in the sky. Remove that light, and you do not simply lose a navigational aid, you lose the teacher. The other bodies in our solar system can teach us what a world without a stabilizing large moon looks like. Mars is the most instructive example. Mars has two moons, Phobos and Deimos, but they are tiny, captured asteroids, too small to exert meaningful gravitational influence on Mars's rotation or axial tilt. And Mars has wandered. Its axial tilt has shifted chaotically over millions of years, ranging between near 0 degrees and potentially as high as 60 degrees in its past. When Mars tilted toward higher obliquities, its poles would have received direct sunlight for prolonged periods, warming enough to sublimate the polar ice caps and briefly thickening the atmosphere. Then, as the tilt shifted back, the atmosphere would collapse, the ice would reform, and Mars would become frigid and thin-aired again. This kind of repeated, dramatic climate cycling is inhospitable to the slow, patient process of biological evolution. Life needs time to adapt. It needs relative stability across millions of years to allow complex organisms to evolve, persist, and diversify. Mars never had that stability, and perhaps that is part of the reason that despite being in the habitable zone, despite likely having liquid water in its early history, Mars today is a cold, dry, nearly airless world. Without a moon like ours, Earth might have followed the same path. There's also a subtler lesson in Mars. The atmospheric loss that Mars has experienced over billions of years is partly a consequence of its smaller size and weaker magnetic field. But some researchers argue that the axial instability driven by the absence of a stabilizing moon has contributed to Mars's inability to maintain a thick atmosphere. When the poles tilt toward the sun, ice caps sublimate and the atmosphere temporarily thickens. Then the tilt shifts back. The atmosphere collapses again, and the carbon dioxide refreezes at the poles. This cycling has prevented Mars from building up the kind of sustained atmospheric and geological processes that on Earth have, over billions of years, resulted in the carbonate-silicate cycle, the long-term thermostat that has kept Earth's temperature within the range of liquid water for 4 billion years, despite the sun becoming 30% brighter since Earth formed. Mars has been unable to sustain that thermostat, and so it has slowly died, in the way that all rocky planets without the right conditions eventually die. And then there is Venus. Venus has no moon at all. It rotates extraordinarily slowly, completing one rotation in 243 Earth days, slower than its year. Its axial tilt is essentially zero. It experiences no seasons, and it has runaway greenhouse warming that has raised surface temperatures to 465 degrees Celsius, hot enough to melt lead. The extreme conditions on Venus do not prove that its fate was caused by its lack of a moon, but the contrast is instructive. Earth sits between two worlds that, for different reasons, have failed to sustain life as we know it. And Earth's stabilizing secret, the thing that makes it different from both its neighbors, is that quiet, patient, gray companion in the sky. The moon is also our shield. This fact is less well known than the tidal story, but it is no less important. Jupiter's enormous gravitational field acts as a vacuum cleaner for the outer solar system, capturing or redirecting many of the comets and asteroids that would otherwise threaten the inner planets. But the moon acts as a secondary shield, its surface bearing the scars of billions of years of impacts that might otherwise have struck Earth. Every crater you can see on the moon's surface is a potential catastrophe that did not happen here. The moon absorbs blows. It always has. Think about the Tycho crater, that enormous young impact basin in the moon's southern highlands, 85 kilometers across and nearly 5 kilometers deep, visible to the naked eye on clear nights as a brilliant white splash of ejecta. The asteroid that created Tycho around 108 million years ago, right in the middle of the age of dinosaurs, struck with the force of roughly 2.5 billion nuclear bombs. If it had struck Earth instead, the Cretaceous mass extinction, which wiped out the non-avian dinosaurs 66 million years ago, might have come early, with consequences for the subsequent evolution of life that are impossible to predict, but almost certainly profound. That is just one crater. There are over 5,000 impact craters larger than 20 kilometers on the moon's surface. 5,000 moments when the moon took a hit that might otherwise have been aimed at us. A world without the moon would be a world exposed. Impact rates on the Earth's surface would be significantly higher. some researchers argue that without the moon's gravitational influence clearing some orbital debris from Earth-crossing trajectories, mass extinction events on Earth would have been far more frequent. And mass extinction events, while not the end of life, are deeply disruptive to the specific evolutionary pathways that produced complex, intelligent life. The dinosaurs were wiped out by an asteroid 66 million years ago. Their extinction opened the ecological space that allowed mammals, including our ancestors, to diversify and eventually give rise to humans. But if impact events had been twice as frequent, or 5 times as frequent, the interruptions to complex evolutionary trajectories might have been too great to allow intelligence to emerge at all. The moon is, in a speculative but serious sense, one of the reasons you are here to ask questions about it. There is something almost parental in this relationship. The moon standing between Earth and the violence of the solar system, absorbing what is meant for us, wearing its wounds on its face for all to see. Every crater is a scar it took for us, and we look up at it and see a beautiful, pockmarked face and never quite connect what we are seeing to what it means. The moon has been protecting us for longer than life has existed on this planet, and we barely noticed. There's a story from 1609 that almost nobody remembers. A Dutch spectacle maker named Hans Lippershey had recently filed a patent for a device he called a kijker, a looker, which used a combination of lenses to make distant objects appear closer. News of this invention spread through Europe with the speed that good intellectual gossip has always traveled, and within months it reached a mathematics professor in Padua named Galileo Galilei. Galileo, characteristically, immediately set about building a better version. By November of that year, he had turned his improved instrument toward the sky and made a series of observations that would permanently alter humanity's understanding of its place in the universe. He observed the moons of Jupiter. He saw the phases of Venus. He mapped the surface of the sun, carefully tracking sunspots across its face. But among his very first observations, before any of those more famous discoveries, Galileo looked at the moon. What he saw surprised him. The moon was not, as the prevailing view had it, a perfect, smooth sphere of celestial material, categorically different from the corrupt and imperfect matter of the earth. It was rugged. It was pitted. It had mountains and valleys and what appeared to be great flat plains that Galileo called Maria, seas, though he correctly suspected they contained no water. The moon, he reported, was more similar to the Earth than anyone had imagined. He published his observations in a small book called Sidereus Nuncius, the Starry Messenger, in 1610. It sold out immediately, which was remarkable for a scientific publication. People understood even then that something fundamental had shifted. The moon was not elsewhere. It was not beyond reach or beyond comprehension. It was a place, a world, and it was ours. 4 centuries later, in July 1969, 12 human beings would walk upon that world. They brought back rocks. They left behind footprints that, in the absence of wind or rain or any erosive force, will still be there in 1,000,000 years. They planted a flag that has since been bleached white by radiation, which is a kind of cosmic irony. And they placed retroreflectors on the surface that scientists still bounce lasers off today, measuring the exact distance to the moon with millimeter precision. That is how we know it is drifting away at 3.8 centimeters per year. We know because we measured it, precisely, repeatedly, with lasers. And knowing that number, Knowing the exact rate of the moon's retreat, we can run the calculation in reverse and confirm what the giant impact hypothesis already told us. About 4.5 billion years ago, the moon was right here, right where we are now. Its orbit has been expanding ever since. The moon has been leaving us, slowly, for all of history. And the question of what happens when it returns is really a question about what happens when a 4.5 billion year-long departure reverses direction and comes to its conclusion. In February 2024, a team of researchers from the University of Edinburgh published a study in the journal Communications, Earth and Environment that examined the relationship between tidal forcing and the biological clock of intertidal organisms. They found that the circadian rhythm, the internal biological clock that allows creatures to anticipate and respond to tidal cycles, is present not just in obvious intertidal species like crabs and limpets, but also in organisms like sandworms, midges, and even in the molecular timekeeping machinery of cells that are never directly exposed to tides. The implication is that the tidal cycle, driven by the moon, has left its mark not just in the behavior of coastal species, but in the fundamental molecular architecture of life itself. The moon is written into biology at a level far deeper than we previously appreciated. This discovery is not surprising when you consider the timescales involved. The moon has been generating tides on Earth for 4.4 billion years. Life has been evolving in response to those tides for most of that time. The circadian clock in your cells, the one that tells your body when to be alert and when to sleep, when to release certain hormones and when to suppress them, has its deepest evolutionary roots in ancestors who were themselves responding to the tidal rhythms that the moon imposed on ancient oceans. Your biology remembers the moon even in moments when you do not. The moon has also been a partner in navigation for as long as humans have sailed. For the vast majority of maritime history, from the earliest Polynesian voyagers crossing the Pacific to the European explorers of the Age of Sail, the moon was one of the few reliable tools for determining longitude at sea. The method of lunar distance, measuring the angle between the moon and a known star, and calculating from that the precise time at the Greenwich meridian, which could then be compared to local time to determine how far east or west you were, was the primary technique for oceanic navigation before accurate chronometers became widely available. The great charts of the Pacific, the detailed maps of the Indian Ocean, the navigational confidence that allowed ships to cross thousands of kilometers of open water and arrive at intended destinations were built on centuries of precise lunar observation. The moon charted the world for us. And then there is the moon's influence on the most ancient biological processes. Coral reefs spawn in synchrony with the full moon in what is one of the most spectacular biological events on the planet. The mass spawning of the Great Barrier Reef, in which billions of coral polyps simultaneously release their eggs and sperm into the water in a great underwater blizzard of reproduction, is timed to occur on the nights following a full moon in late spring when water temperatures reach a certain level. The light of the full moon triggers the spawning. Without that trigger, the synchrony breaks down, and synchrony is essential because the eggs and sperm of different coral species need to meet in the water column, and they can only do that reliably if every individual spawns at the same time. A world without the moon, or with a disrupted lunar cycle, would be a world in which coral reefs are unable to reproduce effectively. the largest biological structures on Earth, structures that support a quarter of all marine species, despite occupying less than 1% of the ocean floor, depend on the moon for their continuation. Dung beetles navigate by the light of the Milky Way on moonless nights. But on bright moonlit nights, they navigate by the moon, using it as a fixed reference point to roll their precious cargo in straight lines away from the dung pile before competitors can steal it. Sea turtles use the brightness differential between the moonlit sea and the dark land to navigate from their nests to the ocean on the night they hatch. The moon is their compass. Nocturnal predators time their hunts to the lunar cycle, becoming less active on bright moonlit nights when they are visible to prey. Nocturnal prey species do the same, hiding when the moon is full and venturing out in the dark of the new moon. The entire structure of nocturnal ecological relationships is partly built around the lunar cycle. The moon is embedded in the behavior of life on Earth at every level of the food web. Let us, for a final time, return to the sky above the moment of impact. Not the drawn-out millennia of the ring formation and the bombardment, but the moment, some perhaps billions of years hence, when the last large fragment of what was once the moon strikes the last cool surface of what was once the Earth. In that moment, from the standpoint of any hypothetical observer orbiting at a safe distance, there would be a brief and brilliant flash, then an expanding cloud of vapor and rock. Then, slowly, gravity would begin its patient work of reassembly. Over millions of years, the debris cloud would cool and condense. A new rocky body would take shape, somewhat larger than the old Earth, perhaps with a small ring or rings of leftover material. Its surface would be fresh rock, still cooling. Its interior would be vigorously active, heat from the impact energizing a new era of volcanism and tectonics. And from that fresh volcanic rock, from the water-bearing asteroids that continued to drift through the system, from the organic chemistry that has never needed very much to get started, the process might begin again. Not certainly, not inevitably, but possibly. Because the universe's most stubborn feature is not its size or its age or its violence. It is its tendency, wherever conditions allow, toward increasing complexity, toward chemistry that reaches for more chemistry, toward structures that organize and replicate and evolve. The story of Earth is a story of catastrophes survived, of extinctions that cleared the way for new flourishings, of Thea's ancient impact that made the moon, and of the moon that made us. If the moon returned and the story started over, the new story would be different, unimaginably different. But it might, in the end, tend toward something. It might tend toward wonder, and so you find yourself back where you started, standing on a planet that is still here, still turning, still gently rocked by the tidal forces of that pale companion in the sky. The moon is there right now, 384,400 kilometers away, drifting outward by the length of a finger every year, moving away from you so slowly that no human lifetime will ever perceive it, but moving, faithful, ancient, shaped by the same catastrophe that shaped this world, and shaping this world in return, every hour of every day, through the tides and the rhythms and the stabilized seasons and the gravity that keeps the oceans from wandering too high. The moon is not just a rock in the sky. It is the reason the sky looks the way it does. It is the reason the oceans exist in the form they do. It is the reason the day is 24 hours long. It is the reason the climate has been stable enough for complex life to evolve. It is the reason your distant ancestors learned to count, and then to calculate, and then to build telescopes and space programs and orbital mechanics equations precise enough to land people on its surface and bring them home. The moon is in your biology, your calendar, your language, your mythology, your first steps toward understanding the universe. It has always been there, and you have always, in ways you never quite realized, been shaped by it. The question of what would happen if it hit Earth is really a question about what the moon has given us, and the answer is almost everything. Look up on a clear night. There it is, closer than it has any right to be, more important than you ever thought to ask. The moon. But perhaps the most profound thing to take away from this entire thought experiment is not the scale of the destruction that would follow the moon's return. It is the realization of just how unlikely our existence is. There are perhaps hundreds of billions of planets in the Milky Way alone. Of those, many are in the habitable zones of their stars, where temperatures could, in theory, allow liquid water. Of those, some may be rocky, like Earth, rather than gaseous, like Jupiter. But of those rocky, potentially water-bearing worlds, how many have a large, stabilizing moon formed in exactly the right way, from exactly the right impact, at exactly the right time, in the right orbit? How many have that moon persisting at the right distance for long enough to allow complex life to evolve, to make it through multiple mass extinctions, to eventually produce creatures capable of standing on their own world, building metal machines, launching them into space, and landing them on that very moon? The answer may be very few. The formation of a large moon through the giant impact mechanism appears to require a specific set of circumstances that are not common. The impactor Theia had to be roughly the right size. It had to strike at roughly the right angle. The resulting debris disk had to have roughly the right composition and angular momentum to produce a moon in a stable, moderately inclined orbit, rather than a chaotic swarm that would have dissipated back into space. Every one of those conditions had to be met, and they were. Here, for us. The moon is, in this sense, not just a geological or biological fact of Earth's history. It is a reminder that our existence is contingent, that the universe did not have to arrange itself this way, that the chain of improbable events that produced you is so long, and each link so unlikely, that the appropriate response to looking up at that pale disk in the sky might be something closer to astonishment than casual familiarity. We have grown accustomed to the moon the way we grow accustomed to anything that has always been there. We forget that it is extraordinary. We forget that it is ours. And we forget until someone asks a question like this one, just how completely and irreversibly everything would change if it were not. So the next time you look up on a clear night, give it a moment. That pale, pockmarked disk floating above you has been there for 4.5 billion years. It stabilizes your world. It times your tides. It slowed your day to a length that life could use. It shields you from blows you never see coming. It taught your ancestors to count and to navigate and to wonder. It is leaving you slowly and will continue to leave you for billions of years to come. And it has never, not once in all that time, asked for anything in return. There it is, closer than it has any right to be, more important than you ever thought to ask. The moon. But it is also worth asking what that question, if the moon hit Earth, really means at a deeper level. Because the question is not really about catastrophe. It is about dependency, about what we are, and what we have, and what we take for granted. It is the same kind of question as, what if oxygen disappeared for 5 minutes? Or, what if the magnetic field reversed overnight? These questions strip away the assumptions we make about the stability of the world, and in doing so, they reveal the extraordinary improbability of the conditions that make our existence possible. Every civilization in recorded history has had a relationship with the moon. The Egyptians worshipped Khonsu, the moon god who measured time. The ancient Sumerians tracked the moon's phases with an accuracy that still impresses modern astronomers. The ancient Chinese divided the year into months, calibrated to the lunar cycle. The Islamic calendar is purely lunar. The Hebrew calendar is lunisolar, combining the cycles of both the moon and the sun. The Buddhist calendar, the Hindu calendar, the traditional Celtic calendar, virtually every pre-modern system of timekeeping on Earth is organized around the moon. We did not choose this because someone decided it was convenient. We chose it because the moon is the most obvious and reliable clock in the night sky, and our ancestors were practical people who used the tools available to them. The moon was the first clock, the first calendar, the first shared reference point around which the human experience of time was organized. Remove the moon, and you do not just alter the tides. You alter the way humanity has, for all of recorded history, divided and experienced time itself. You remove the word month from every language. You undo 10,000 years of calendar making. You erase the navigational traditions of every seafaring culture that has ever existed. Every poem ever written about the moon. Every painting ever made of moonlight on water. Every love song that invokes the lunar cycle. Every superstition, every festival, every tide table, every maritime chart, every biological clock ticking quietly in your cells. All of it, in one way or another, is a consequence of a collision that happened 4.5 billion years ago, when a Mars-sized planet struck the young Earth and flung a disk of debris into the sky that coalesced slowly into the world's most faithful companion. And so to answer the question, if the moon hit Earth, everything ends. The tides become catastrophic. The crust fractures. The ring forms and falls. The bombardment strips the surface. The atmosphere becomes a furnace. The oceans evaporate. The record of 4 billion years of life is sealed beneath a new planetary crust. And then, after millions of years of slow reconstruction, perhaps it begins again. Different, unrecognizable, but perhaps in the deep logic of chemistry and gravity, still tending toward something. The universe has a habit of trying. Look up on a clear night. There it is, closer than it has any right to be, more important than you ever thought to ask. The moon. You've been watching If the Moon Hit Earth. Don't forget to like and subscribe and leave us a comment to let us know what you think. Thanks for watching, and we'll see you next time.